Exponential functions. This is something you've probably seen in previous algebra classes. It gets covered in many times over. So an exponential function with base b, we can define as f of x equals b raised to the power of x. The critical thing with an exponential function is that the variable's in the exponent, and then the base of the exponent is going to be a number. It has to be greater than 0, but not 1. So any positive number except 1. We can break exponential functions down into two different types, what we call growth and decay functions. If the base of the exponents are larger than 1, we get the growth function. It's increasing as you look at it from left to right. And two nice points you can find on this function. If x is 0, we get b to the 0 is just 1. And if x equals 1, y equals b to the 1, which is this b. And so those are two easy points to find on the function. And then the exponential function is going to have a horizontal asymptote along the x-axis, also known as y equals 0. Now, if the base of the exponent is a fraction between 0 and 1, then we're going to get what we call a decay function, where it's decreasing as we look at it from left to right. It will still go through the same 2 points. I'll have the y-intercept of 0, 1, and the nice point at 1b, only b now is a number between 0 and 1, so it's a little bit harder to locate there. And again, we get the horizontal asymptote. So these are going to be smooth and continuous functions. They have the y-intercept at 0, 1, and then an easy-to-find point at 1b, whatever b might be. Horizontal asymptote at y equals 0. The domain of exponential functions are negative infinity to infinity, all real numbers, whereas the range go from 0 to infinity, but they never actually reach 0, so we don't include 0 in the range. And these are one-to-one functions, so they will have an inverse, which will be real important for the next section. Okay, so first I'm going to graph the basic function 2 to the x. 2 is just an easy one to work with. So I've got a base of 2, which is larger than 1. And then if I let x equal negative 2, negative 1, 0, 1, 2, I can calculate my values for y. And just a reminder, with negative exponents, 2 to the negative 2 would be 1 over 2 to the positive 2, so that'd give us 1/4. And so that's my black curve here, plotting these points of negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, and then connecting the points up with a smooth continuous line and a horizontal asymptote along the x-axis. And then some variations. The red line here is the graph of f of x plus 1, so 2 to the x plus 1, which we know will shift the graph up 1 unit, which is going to shift the asymptote up 1 unit also. And so our domain is still negative infinity to infinity, but the range is from 1 to infinity. I think you can see that as we shift each point from the black line up 1 point and we get a point on the red line, we can see how we're getting this asymptotic behavior as we go off towards negative infinity. The y values get closer and closer to 1. And then the green line is f of x plus 3. So inside the function, we've modified the independent variable 2 to the x plus 3. This is going to shift the graph left 3, which isn't going to change our domain and range and isn't going to change our horizontal asymptote, because if we slide the horizontal asymptote over 3, it's still in the exact same place that it was. A couple more transformations. Again, the black line here is my basic 2 to the x, and a little hard to see here. So this is f of x is 2 to the negative x, which is going to reflect over the y-axis. That's my red line here. So the same graph shifted over the y. And then let's look at the blue line next. Negative f of x, that's going to shift it over the x-axis. There's my blue line here, all these points flipped over, which is going to change my range. My range is now from negative infinity up to, but not including 0. And then 3 times 2 to the x, 3 times f of x will stretch the graph vertically by 3. And so my nice point at 0, 1 is now at 0, 3. My nice point at 1, 2 is now at 1, 6. Each of the y values is being tripled, and I still have the same horizontal asymptote here. Okay, the natural exponential function is what we call f of x equals e to the x. E is a number so special, it's actually got 2 keys on the calculator. One is e to the x, and one is just a plain e. The formal definition of e is the limit as x gets very, very big of 1 plus 1 over x to the x. If you're interested, you might put this into your calculator, take a look at the table, and see what happens as x gets larger and larger. It's kind of interesting. What it's going to do is approach this number, 2.7182818. It goes on forever. It's a non-terminating, non-repeating decimal like pi. It's an irrational number. It's difficult to write down, but it gets used in a lot of applications, and so we created a new symbol for it, the letter E. Okay, so classic application is the exponential growth model. We use this for interest compounded continuously. We also use the same formula for populations that grow exponentially. P is the initial amount, so the initial deposit or initial population. R is the interest rate or population growth rate. A is time, might be in years, might be in minutes, etc. So our example here, we deposit $4,000 in an individual retirement account. We let it sit there for 20 years, where it's compounded at 4.25% interest. Those were the days. So you can plug it into your calculator and get the total amount in the account after 20 years. That's a little more than doubled it for 20 years.